Let us begin by recalling what we were trying to do. So we observe that if X is a manifold, smooth manifold, and U contained inside X is an open set, is a coordinate open set with coordinates x1, x2, and so on up to xn, then over U, the tangent bundle Tx restricted to U is isomorphic to the trivial bundle U cross Rn. And where, so this has the projection map to U, where the trivialization is given using the sections Si defined by as Si of P is defined to be d by dxi at P. And we were wondering if is the converse true. That is, given an open set U contained in X such that Tx restricted to U is trivial, does this imply that there are global coordinates on U? So to answer this question, we first gave a smooth structure okay, so before that, suppose X is a smooth manifold and G contained in automorphisms of X. So recall that automorphisms of X is those bijective maps phi from X to X, says that phi is a diffeomorphism. Such that when I consider the map pi from X to X mod G, this is a covering map. So X mod G has the quotient topology. Is a covering map. Then there is a natural manifold structure or differentiable structure on X mod G with respect to which pi becomes a smooth map and it's also locally so let me just write it as and a local diffeomorphism. So by a local diffeomorphism, we mean that given uh, x in X, there is a neighborhood U such that pi from U to pi of U is a diffeomorphism. So let's just quickly see how we did this. So the main point to note was that given any point P in X mod G, there is a neighborhood V which contains P, which is evenly covered. And so for this V, we have pi inverse V breaks up into sheets, and each of these sheets each of so if I fix one sheet, all these sheets are translated onto each other by elements of G. So if I make my V over here, so then the inverse image breaks up into sheets, and I can fix any one sheet U, and all the other sheets, all other sheets all other sheets are obtained as G translates of U. And using this, just for any V, fix one sheet U, then the map pi from U to V is a homeomorphism. And by shrinking V if necessary, or by shrinking V, we may let me write by shrinking U V and hence U, we may assume that U is a coordinate neighborhood. And then using pi, we give a differentiable structure. We can transfer the differentiable structure from U to V. And we need to check that the compatibility. So the point is that if I take a set V1 and if I take a set V2, then the inverse image of V1 is going to break up into sheets like this. So let's say U1, we picked up this sheet U1, and now the inverse image of V2 is also going to break up into sheets like this. Let's say for U2, we pick this sheet. So what we need to show is let me call this set A, and let me call this set B. So we need to show that this is pi restricted to u1, this is pi restricted to u2. So pi restricted to u2 and then apply pi restricted to u1 inverse this from pi restricted to u2 inverse of v1 intersection v2 to pi restricted to u. So that's exactly B. From B to A is a diffeomorphism. But now notice that when we take pi inverse of v1 intersection v2, this also breaks up into sheets, and all the sheets are given by translates of, let me call this part C. Some G, sorry. Okay, so G, we don't need a C over here. So is all these are G translates of this set A. So in particular, to show that, okay, so in particular, there exists G in G such that G of A is equal to B. Now let's write it the other way around, or translates of B. So we need to show that pi restricted to u1 inverse compose pi restricted to u2 from is actually equal to G. So the restriction of this whole thing to B is equal to G restricted to B. But when we restrict to u1 and u2, all these maps pi restricted to u1, pi restricted to u2, and G are all bijective maps. So this happens if and only if pi restricted to, let's say, B is equal to G restricted to B composed with pi restricted to B. But this is obviously true. Since the diagram commutes. So since G is a diffeomorphism of X, this implies pi restricted to u1, our condition composed pi restricted to u2 is smooth, is a diffeomorphism. So thus, this implies X mod G has a smooth structure with the required properties. And let's also make A simple observation lemma: let pi from x to y be a covering map, which is a smooth map between smooth manifolds. Well, this is not enough, so let me just change this. Let pi to x mod g. P P as above. Then pi lower star from tpx to t pi of p x mod g is an isomorphism. And the proof is obvious. This is clear since pi from u to v is a diffeomorphism. By definition. So next let us prove that. So next we want to prove this proposition. The tangent bundle of S1 is trivial. It's a proof. So the tangent bundle of S1 is a vector bundle of rank 1. Thus, to show it is trivial, it is enough to construct a section or to find a smooth section so I have ts1 s such that s of p is a non-zero vector for all p in S1. And because then by whatever our previous exercises, we will get that S1 cross R to TS1 P comma lambda maps to lambda times S of P is an isomorphism of vector bundles. So we will show that such a non-vanishing section exists. Show that such a section exists. So we know that, okay, so let f from R to R mod Z denote the covering map. So we can think of it as t goes to e to the power 2 pi I t. And assume that R mod Z has been given the differential structure as explained before. So we know that there is a commutative diagram. So this is the tangent model of R, and this map we called F tilde to the tangent model of S1, S1. And we know that the tangent model of R is trivial. So because of that, there is a section S of a point P is defined to be d by dx at P. So since so because of our earlier lemma, this lemma, we know that f tilde lower star from T PR to T f of P S1 is an isomorphism. And we also know f tilde is smooth. So this implies that the section the map f tilde compose S from R to TS1 is a smooth map. Such that for all P in R, f tilde compose S at P is not equal to 0. So in order to check, so let's just consider this abstract statement. If pi from x to x mod g is as above, or let me rephrase this. Let's consider this statement. Suppose h from x to y is a smooth map such that h compose g is equal to h for all g in G, then clearly h descends to give a smooth map x mod g to y. So in terms of a diagram, we have x to y, we are given h, and h has this property. That means that this map will factor like this. This is a pi. So the proof of this simple observation is left as an exercise, and using this observation, it only remains to check that under the action of Z on R, the section F tilde compose S is invariant. So let pi n from R to R denote the translation by n map. So phi sub n of x is defined to be x plus n. Then we need to show that f tilde compose S compose phi sub n is equal to f tilde compose S. So it is trivial to check that S compose phi sub n is equal to phi n tilde compose S. And moreover, we also have that f tilde compose phi n tilde is equal to f compose phi n tilde. So thus, when we combine these two observations, we get f tilde compose S compose phi n is equal to f tilde compose phi n tilde compose S is equal to f compose phi n compose S. But f compose phi n is simply equal to f. This implies f tilde compose S descends to give a section of the tangent bundle of S1, and this section, so let me call it S prime, and S prime of P is not equal to 0 for all P in S1. This proves that TS1 is a trivial bundle. However, does there exist a global coordinate on S1? So what this means is there a map y from S1 to R such that the image of y is open and y from S1 to y of S1, so let's call this open set U, say U, or call it W in R, and such that y from S1 to W is a diffeomorphism. So clearly this is not possible, as the image of any continuous function is going to be closed. For any continuous function y is closed, is compact, is closed and compact, and so cannot be R1. And so cannot be open, sorry. Open in R. So, as I had mentioned in the previous lecture, that we have now given two differentiable structures on S1, and one has to check that these two are the same, but that's not such a difficult exercise, and that's not so difficult to see, and that's left as an exercise. Okay. So now we want to do, so having seen this example, which kind of illustrates some of the ideas which we have seen so far, uh, some applications of the ideas we have seen so far, let us proceed to do some constructions with vector spaces. So our aim is to do these constructions for vector bundles, but we will start by recalling them for vector spaces. Let V and W be vector spaces over a field K. Then there is a vector space V direct sum W. Similarly, there is a vector space V tensor N. The elements, so the tensor product is being taken over K. So the elements of V tensor N, so we will often suppress the notation K when that is clear, are of the form summation I equal to 1 to R Vi tensor Wi, where Vi and Wi belong to V and W, and they satisfy the relations. So there are three kinds of relations. AV tensor W is equal to A of V tensor W. V tensor AW is equal to A of V tensor W. So here A belongs to K, and C V plus W, I'm sorry, V1 plus V2. So let me write this over here. V1 plus V2 tensor W is equal to V1 tensor W plus V2 tensor W, and V tensor W1 plus W2, V tensor W1 plus V tensor W2. So one way to define, a very general way to define V tensor W is to do it as follows. First, we take the free vector space on this set. So we just take all pairs v and v comma w, where v is in v and w is in w, and we go modulo relations of the type a, b, and c. So in other words, uh, the free vector space is the vector space. This vector space F is the vector space. With basis E sub v comma w, and with relations E a v comma w is equal to a times E v comma w is equal to E v comma aw. That's one relation, and similarly we have the other relation E v1 plus v2 comma w is equal to E v1 comma w. So this is my A, my P plus E v2 comma w. So maybe I should write minus over here. Comma minus. And similarly we also have C. So it is easily checked that if EI is a basis for V and WJ is a basis for W, then I'm sorry, EI and let's say FJ. Then EI tensor FJ is a basis for V tensor W. So in particular, if both P and W are finite dimensional, then the dimension of V tensor W is a product of the dimensions. So you may contrast this with dimension of V direct sum W is the sum of dimensions. So the vector space the vector space V tensor W has a certain universal property. So this is the following. So first note that there is a map from V cross W to V tensor W. Now let me write it horizontally. So this map just sends a pair v comma v comma w to v tensor w. And this map is k bilinear. Now if t from v cross w, or let's say a from v cross w to u is any bilinear map, any k bilinear map, then it factors uniquely as so here sorry. So there is a one-to-one correspondence between a and a tildes, and a tilde on the pure tensors v tensor w is defined to be, is forced to be, if you want this diagram to be commute, if you want this diagram to commute, a of v comma w. So if you give this map some name, let's call this pi. Call this pi. So and we also check that a tilde is k linear. So this, let's write this as a proposition. So let's look at the two sets, k bilinear maps. From v cross w to u, and k linear maps from v tensor w to u. And pi sets up a bijective correspondence between these two. So what is the proof? So the idea is very simple, and we just use the construction of v tensor w, and I will only explain how to show the existence of a tilde from a. So first define, let's say, a tilde from the free vector space on all bases on this set, to u as a tilde of v comma w is just equal to a of v comma w. And since a is k bilinear, check that the relations a, b, c are in the kernel of a tilde. So this implies that a tilde factors to give a map v tensor w. So I'll leave the details to you. And clearly a tilde is linear. So let me just make a remark. So okay, let me just write it here. I mean, clearly a tilde is k linear. Let me make a remark. This construction and the above proposition can be generalized two vector spaces. V1, V2 up to VR to give a space V1 tensor V2. VR. And there is a similar universe. So there is a similar universal property with respect to K multilinear maps. So when all the VI's are the same vector space V, then we denote V tensor V tensor V by V tensor R. So we may put all these together, all these together to get an algebra. Which we call the tensor algebra. So this is just, I just take K, direct sum V, direct sum V tensor V, direct sum V 3 times and so on. So what is the algebra structure? So we need to define a multiplication. So we define T star V, the product to T star V. So it's enough to define it on the pure tensors and then we will extend it linearly. So suppose I take two pure tensors, V1 tensor V2 tensor VR and V1 prime tensor V2 prime tensor Vs prime. Then we multiply these two in the obvious way and it gets sent to V1 tensor V2 tensor VR tensor V1 prime tensor V2 prime tensor Vs prime. So this is in V tensor R, this is in V tensor S, and this lands in V tensor R plus S. So clearly this is an associative graded. So the grading is given by Z. So this is the degree 0 elements. This contains the degree 1 elements. This is the degree 2 elements. This is the degree 3 elements, and so on. And the multiplication clearly has a nice property with respect to the grading. This is not commutative. K algebra. with 1, with an identity. So the degree 0 term contains the scalars, and the scalars are multiplied in the usual way. So this is the tensor algebra of V. And now inside the tensor algebra, there are two special ideals. So there are the two ideals. So let's denote the first one by I of V. So this is defined to be the two-sided ideal generated by elements of the form V tensor W minus W tensor V. And the second ideal is, let's call it J of V. This is the two-sided ideal generated by elements of the form V tensor W plus W tensor V. So clearly, both the ideals are graded and so thus we get an algebra T star V mod I of V and T star V mod J of V. So let's look at the first one. T star V mod I of V is graded commutative. Algebra denoted by S star V. And the Rth graded piece of S star V is denoted SRV. And the most important point is, if V is a finite dimensional vector space with basis EI, so let's say E1 through En, then can be easily checked that a basis for SRV is given by tensors EI1, EI2, EIR, where similarly the algebra T star V mod J of V is denoted by lambda star V and called the exterior algebra of V. So this is called the symmetric algebra of V. And the multiplication has the following property. So we have a multiplication map. So this is simply the multiplication map on the tensor algebra induces a multiplication map on the exterior algebra. So it's denoted by alpha comma beta maps to alpha wedge beta. We write it like this. And it satisfies the following property. If alpha is in exterior, let's say degree of alpha v, and beta, alpha and beta are homogeneous elements, then alpha wedge beta is equal to minus 1 to the power degree of alpha times degree of beta into beta wedge alpha. And once again, if V has basis E1, E2 up to En, then the Rth exterior of V has basis EI1, EI2, tensor EIR, where so in particular this implies that if R is strictly greater than N, then exterior RV is equal to 0. And exterior NV is isomorphic to K and generated by E1 wedge, E2 wedge, wedge En. So we stop here. We will stop here. In the next lecture, we will carry out similar constructions for vector bundles. For vector bundles.